So in this lecture, this is a new topic. This is a new chapter. So this is chapter 3 on weight-volume relationship. Remember, this is our basic roadmap, our course objective list. In weight-volume relationship actually is directly related to several of our course objectives, including compaction. So for compaction, you need to know the dry unit weight of soil. For soil permeability, seepage, you need to know void ratio, porosity, you need to know water pressure. And then for total effective stress, so you need to know the unit weight of soil, which is a weight volume relationship problem. And then for consolidation, you definitely need unit weight. You need to estimate stress change. So many of these course objectives are directly related to what we are going to talk about today. So the first thing I want to point out, in that Shelby tube, when you take soil sample from the field in its natural state, soil is actually a multi-phase material. Okay. And most commonly, natural soil is formed of 3 phases. And the first one is obvious, it's solids. So you have the solid particles, that's the first phase. Okay. And natural soil typically has some moisture content, has some water. So the second phase is water. And then the last phase is in between those voids in between those solids where the voids are not occupied by water, you have air. So the third phase is air. Okay. So natural soil typically consists of these 3 phases, solids, water, and air. And solids are typically the most important one. So solids dictate the engineering properties of soil, how strong it is, or how deformable it is. And many of the engineering properties of soil depend on basically how densely solids are packed and how much water is present in voids. Okay. And to quantify this, we use what we call phase diagram here. And phase diagram in different textbooks, sometimes people call this block diagram. They say the same thing. And I'll explain what this diagram is basically. Okay. So we use this phase diagram. This is a tool we use to basically quantify the relative amounts of each phases and then develop this weight volume relationship. So what this phase diagram look like? So on this slide, there are 2 figures here, basically. On the left-hand side, that's soil in its natural state. So you have all these irregular shaped solids, particles, you have all these voids. Some of the voids are filled with water, some are filled with air. So that's a natural soil. And on the right-hand side, that's the phase diagram. So this phase diagram, basically, if you look at this diagram, there are 3 different phases. So those are the 3 phases we just mentioned. So you have solid, and you have water, and you have air. Okay. So this phase diagram basically it's an idealization of that natural soil. So we put all solids into one phase, all water into one phase, and all air into one phase. And we use this to calculate their relative amount. So there are many symbols here, so I'll explain all these symbols one by one. Okay. So let's zoom in a little bit here. Again, we have 3 phases, solid, water, and air. Okay. So on a phase diagram, you have what we call weight side and volume side. So I quantify and basically mark all these different phases on both sides. So we have weight, and then volume. Okay. And for weights, we're going to use W, let's say capital W for weights. And since there are different phases and we have different weights for solids, we use WS, so subscript S for solids. So that's the weight of solid. And then for water, we call this W, that's a weight of water. Subscript the W for water. So that's a weight of water. And then we ignore the weight of air because weight of air is so small compared to the other two phases. So on the phase diagram, we don't consider the weight of air. So the total weight of this soil, we call this W. Okay. So the total weight is the sum of WW and WS. Okay. So this is the weight side of the phase diagram. So we have weight of water, weight of solid, and total weight. And then on the volume side, so again, I'll start with the solid phase. I mean, on the volume side, I'll start with the solid phase. So for the volume of solids, I'm going to use V sub S. So V for volume and subscript S for solids. So that's the volume of solids. And then W, this water here is V of water. And we do need to consider the volume of air. Although it's very light, it does occupy the void space. So we use V sub A for volume of air. Okay, so that's volume of air. And then volume of air and volume of water together, they occupy, basically air and water together, they occupy the void space. So this is called volume of void. Okay. So volume of voids, again, consists of volume water, volume air. So that's volume void. And then the total volume, this is capital V. So that's the total volume. Okay. So total, so this is total weight. And this is total volume. Okay. Volume of voids plus volume of solids. And volume of voids is volume of air plus volume of water. Okay. So that's the phase diagram basically. So you have this phase diagram, you have this weight side and volume side, and you basically mark the weights and volume of different phases on this phase diagram. So that's phase diagram. And then, as I mentioned, for most natural soil, there are three phases: solids, air, and water. So that's the one on the left-hand side. So this is moist soil. So soil, some of the voids are occupied by water, some are occupied by air. So that's true for most natural soil. And on the right-hand side, this is a phase diagram for what we call saturated soil. So saturated soil basically means all the voids are occupied by air. So that's called saturated. And there are only two phases for saturated soil. So there's no air phase. So for saturated, you have solid and water. And on the volume side, you have volume of water and volume of solids. Okay. So that's for saturated soil. And when you're solving weight volume relationship problems, so you need to first identify if that soil is moist soil or it's a saturated soil. So that will determine how many phases you should use on your phase diagram. Okay. So that's phase diagram. And then for, as I mentioned in the beginning, phase diagrams basically gives you the weights and volumes of each phase in the soil. And then we use the phase diagram to develop weight-volume relationships. There are basically 6 main groups of definitions. So I divide all the definitions into 6 main groups. And these are the definitions you should at least know and memorize. You don't actually need to refer to the textbook or anything. So those are very basic definitions. And among these 6, 3 are weight ratios and 3 are volume ratios. Okay. So I'll explain all these 6 main groups of definitions, and then we'll look at some examples. The first one here, the first group of basic definition is unit weight. So unit weight, there are actually different types of unit weight, but they're all weight over volume. They're just different weight over different volume, but they're all weight over volume. And there are a number of different unit weights. The first one, this is called the total unit weight. So total unit weight is total weight over total volume. Okay. So if I use the symbols we just defined, so this total unit weight gamma, I'm going to use gamma T here, is total weight over total volume. Okay. And this total weight we just defined is basically weight of solids plus weight of water over total volume. Okay. So I'll add note here. So unit weights are all weights over volume, just different weights and different volume. So this is total unit weight definition, total weight over total volume. And if soil is saturated, as I mentioned, all the voids are occupied by water. So the saturated unit weight we call gamma SAT for saturated. And its definition is the same, total weight over total volume. And the typical range for saturated unit weight for natural soil is 115 to 135 pound per cubic foot. Okay, so this is pound per cubic foot. Okay. So that's typical range of saturated unit weight for natural soil, 115 to 135. And then if soil is moist, we call that unit weight moist unit weight. And this is typically written as gamma M, M for moist. And again, definition is the same, total weight over total volume. And typical range for moist unit weight for natural soil, 105 to 125 PCF. Okay. So this is the first unit weight called total unit weight. And then for saturated and moist, we have saturated and moist unit weight. In the second unit weight, this is called dry unit weight. Again, weight over volume, but this time it's weight of solids over total volume. And for dry unit weight, we call gamma D. And it's weight of solids. Using our symbol, this is WS. And total weight is capital V here. Okay, so that's dry unit weight. In the typical range for dry unit weight, 85 to 105 PCF. Okay, so that's the typical range of dry unit weight. And I have some notes here about this dry unit weight. So this name may sound a little misleading. You're calculating dry unit weight, but it doesn't mean the soil itself is dry. So you can calculate gamma D for both moist and dry soil. So gamma D basically just quantifies the weight of the solids over the volume the total volume. It doesn't mean the soil itself is dry. So you can calculate gamma D for both moist and dry soil. And that's a common mistake I see. So students tend to think gamma D is just for dry soil. That's not true. So you can have gamma D for moist soil as well. And this is something I mentioned at the very beginning. So one of the course objectives, we're going to look at the soil compaction. And gamma D is actually used to indicate how densely packed solids are. So it's used in compaction specification. So we'll come back to this gamma D in chapter 6 when we talk about compaction. And finally, very few soils in its natural state are completely bone dry. There's almost always some moisture contents in soil. So even if it looks dry, it's going to absorb some moisture content from there. So it's very hard to come across completely bone dry soil. So you always have maybe 1–2% moisture content in your soil. So this is the second of unit weight definition, dry unit weight. And the third one is called unit weight of solids. So this one is weight of solids over volume of solids. Again, you notice that this is weight over volume. So this is one of the unit weight. Okay, for this gamma S, using our symbols, gamma S is WS over VS. Okay. That's weight of solids over volume of solids. And the fourth one here, this is a special unit weight. This is actually a constant. So it's actually a known number for most engineering problems. So if you're given the unit weight of water, you immediately know its value. So unit weight of water in US system is 62.4 PCF, pound per cubic foot. And if you're using the SI system, it's 9.81 kilonewton per meter cube. So that's unit weight of water. And for any problems, if you need unit weight of water, you know that's a constant. I don't need to give you that value. You should remember those two values, 62.4 in the US system or 9.81 in the SI system. So it's a constant. And the next unit weight is called buoyant unit weight. So this is something that will come back on in seepage problem. So this buoyant unit weight, we call gamma B or gamma prime. This is defined as the saturated unit weight minus the unit weight of water. Okay. So remember gamma SAT, that's a saturated unit weight. So saturated unit weight minus unit weight of water. So that's basically the net weight of soil when it's submerged underwater. So that's a unit weight or buoyant unit weight. And just a note here. So all these weight volume, all these unit weights here, they're defined in terms of weight over volume. And the other way to quantify this is to use density. So some problems you will see people use density to quantify this, this relation, basically mass over volume. So density. So all these definitions we defined still apply, but instead of saying, say, unit weight of water, you'll say the density of water. And the unit weight of, the unit weight and the density, they are related through this gravitational acceleration G. Okay. So if you know the saturated unit weight, you can calculate the saturated density. Or if you know the dry unit weight, you can calculate the dry density. So they are basically related to by this gravitational acceleration G. Okay. And the unit of density is kilogram per meter cube. Okay. So that's the first group of definitions, all unit weights. Remember, unit weights are weight over volume. So they're just different weights over different volume. So that's the first basic group. And then the second one here, this is called specific gravity. Okay. So specific gravity, we use G sub S. is basically the ratio of the unit weight of solids over the unit weight of water. Okay. So basically GS quantifies how heavy soils are or that solids are compared to water. So it's a ratio of unit weight of solids over water. And for GS, okay. The unit weight of solids, which is defined this is gamma S. Unit weight of water, which is defined as gamma water, which is, remember, is a constant. And then gamma S, by definition, weight of solid over volume of solids. So that's gamma S definition, then unit weight of water. Okay. So that's specific gravity. And typical range of GS for inorganic soil, 2.6 to 2.8. Okay. And then the next basic definition is void ratio. In this void ratio, we use small letter E. Oops. Okay, yeah. So void ratio here, is the volume of voids over the volume of solids. And E is okay. So that's void ratio. This is the ratio between two volumes. In typical range of void ratio for natural soil, for sands, E is 0.35 to 0.9. And for clays, 0.4 to 1.5. Okay, so that's typical range of voids for sands and clay, void ratio for sands and clay. And number 4 here, this is porosity. Porosity is very similar to void ratio. This is ratio between two volumes. And it's defined as volume of voids, but this time to total volume. Okay. So porosity, we use letter N. Okay. Volume of voids over total volume V here. So that's porosity. Again, if you look at the definition, they're very similar. They're trying to quantify the volume of voids over either the solids or the total volume. And typical range of porosity, and for N value, for sands, it's 0.2 to 0.5. And sometimes people use percentage for porosity. So this will be 20% to 50%. Simply means 20% of the soil are occupied by voids, basically are voids. And for clays, this value is 0.3 to 0.6. Or 30 to 60%. Okay. So that's the porosity definition. And just from the definition, you know these two are related. So it's actually not difficult to derive their relationship here. And for E, okay, it's related to N through this expression here, and vice versa. You can derive N in terms of E. And in geotechnical engineering, I have a note here, void ratio is usually more commonly used. So you see void ratio much more often in geotech compared to porosity. So this is the 4th basic definition, porosity. And then the 5th one here, this is water content, or sometimes it's called moisture content. It's the same thing. Okay. water content or moisture content, they're referring to the same thing. And water content, W is a ratio of weight of water over weight of solids. Okay. And water content is typically expressed in percentage, so times 100%. So that's a definition of moisture or water content. And typical range of moisture content, water content for sand, up to 40%. For clays, 60 or more. So up to 60% or even more. So that's basic definition number 5. So that's water content. And then the last one, this is the last of the 6 basic definitions. This is degree of saturation. And degree of saturation basically measures how much of the voids by volume are occupied by water. So its definition, so S is volume of water over volume of voids. And again, this is typically expressed in percentage, 100%. Okay. So if soil is totally bone dry, there's no moisture in it, there's no water in it, volume water will be 0. So degree of saturation for completely dry soil is 0. Okay. And then for fully saturated, so this is something I mentioned at the beginning of this course. So fully saturated means all the voids are occupied by water. So the volume of water over volume of voids is just 1 or 100%. In fully saturated soil, as mentioned here, can be found below the groundwater table or in a capillary zone. So that's where you typically find fully saturated soil. Okay, so these are the 6 basic definitions of weight-volume relationship problems. And those are the definitions I think you should memorize, you should remember. So these are different ratios. And all the rest can be derived by knowing these 6 definitions and the weight, the phase diagram. And this is a table basically showing void ratio, moisture content, and dry unit weight for some typical natural soil. Okay. So here I'm listing, we're going to go over examples, but here I'm summarizing some keys to solving weight-volume relationship problems. So the first key, as I mentioned, you should know these 6 basic definitions. And three of these 6 basic definitions are basic weight relationships: unit weight, specific gravity, and moisture content or water content. So those are the 3 basic weight relationships. And there are 3 basic volume relationships we just introduced: void ratio, porosity, and degree of saturation. So these are all volume relationships. So you should know all these six basic definitions. And then when it comes to actually solve weight-volume relationship problems, that phase diagram, that block diagram I introduced, that's an important, very useful tool. So you need to learn how to use the phase diagram to solve weight-volume relationship. And again, the best way to learn this is actually through examples. I'll go over quite a few examples in this chapter using phase diagram to solve weight-volume relationship problems. And the first thing we are using phase diagram is to draw correct number of phases. So we mentioned for moist soil, there are 3 phases. In saturated soil, 2 phases. So this is something when you start with solving the problem, you need to know how many phases are there. And you start from one side of the phase diagram, filling in the known, and then cross over to the other side and try to fill out that phase diagram. And unit weight water is constant, so this is always known. So I don't have to present that to you. You don't have for any given problems, even if it's not stated in the problem statement, you should know unit weight of water. And so this point here, there are some problems where everything is given in terms of ratios. So weight ratios, volume ratios. And for these problems, you can actually assume the volume, the total volume is 1 or the volume of solids is 1. Okay. So again, this is something we'll practice through examples. We have about 10 minutes. So I want to go over one quick example and to show you how we use phase diagram to solve weight volume relationship problems. Okay. So we're going to touch all these key points here. Okay. So as I mentioned, for this chapter, this is one of the learning objectives, they say, for this chapter, is to solve weight volume relationship problems using the phase diagram. Okay. If you look at your textbook, there are different equations and formulas. For this chapter, you don't have to memorize those. So all you need to know are 6 basic definitions and how to use phase diagram. So that will allow you to solve all weight volume relationship problems.